So far, like uh, till yesterday, we had seen like introduction to FPGA, architecture of FPGA, how to use Vivado tool, Fortis tool. Also, in one of the session, second session, we discussed what are the various timing issues we will face it in FPGA and how to resolve those timing. And also, we had seen like what is the significance of using synchronizer, what scenario we have to use synchronizer. In yesterday's session, we also seen the debug aspects. Given an FPGA design, in real time, how to debug those systems, right? So debugging is one of the very important aspect we need to focus on because, as I mentioned, like most of the time we spend on debugging rather than design. So the right debugging skill is necessary in FPGA based design. In today's session, I will conclude by showing you like how these IPs are used in FPGA. So one good thing about FPGA is like we have plenty of IP resources or IP uh, libraries which you can use directly in the tools. So this basically helps us to fasten our design. We need not design everything as a system. Like you cannot say that like I'll be designing UART interface, STM, everything I'll write. That is not the case in the real time. So we'll be taking IPs from multiple vendors or like from the Xilinx itself and integrating that into our design, right? So on that aspect, like we will start with a very simple IP. Then I'll show you like what is the real-time IPs available that you can utilize and experiment, and like you can use in your system. And not only that, like uh, your research projects, like many people will do, like I've seen that like lot of papers we publish. So that is not the end point, right? I mean, like let's say like you have designed one Viterbi decode. So you may patent that also. So not only that, I mean, after patenting that IP, you can encapsulate and like encrypt the whole thing, and you can sell it to various companies who are looking for habitability or some communication model, right? So there will be a lot of government projects also which will be going on. So you can actually sell it to them. So how we can package that IP? What are the things we need to keep it in mind like when we are actually packaging those whole IPs, right? So all these aspects, let's discuss. Uh, Let me share my screen. Yes. So when we are talking about IP cores, so we will have various different IPs. So one is actually soft IP. The soft IP is something like we have RTL resources, right? I mean, like we have, I mean, LUT resources, we have registers inside the FPGA. So the soft IP, what it is going to do is you will just write a RTL and you will say that like what are all the netlists of this particular RTL, and your tool is going to select these resources, lookup table or registers or block RAM, and the placement of those components are not fixed. So it is going to use the FPGA resource and it is building the functionality. Let's say like you designed one FFT IP. Okay. So that FFT IP, when you synthesize on the Vivado, so it is going to choose the lookup table, it is going to choose the register, DSP slices, and it can place anywhere in the FPGA. So firm IP or hard IP, whereas like this is something like these resources already created as a circuitry inside there. Let's say like yesterday I was talking about system on chip, where ARM processor, quad core ARM processor, that is a hard IP that is already present in the FPGA. So you are not going to use LUTs registers inside the FPGA and going to create that firm IP, right? So hard IP. So basically, the thing is, we are actually like whenever we are designing, so we have to choose. I mean, we have to choose a FPGA such a way that like what is our requirement. Okay. So yesterday we saw that like SoC we designed that is using hard IP, like ARM was hard IP. But now let's say I don't want that hard IP. Okay. So we have like inbuilt, like we have IPs like in the Vivado called microblade, where you can instantiate that microblade as a soft IP and you can create your own process. Okay. But can someone tell me what could be the uh, difference between hard IP and soft IP? I mean, what is the impact on our design? What could be impact on our design using hard IP and soft?
Speed will be
So
better in case of hard IP.
correct. Basically, speed will be better because it is already it is confined within a small region, right? And whatever the speed aspect, it is already taken care in the ASIC design stage, right? But whereas in the soft IP, what we are going to do is like we are going to utilize the existing resource, and like one part of your IP may be placed in like one of the coordinate, one corner of the FPGA when placement and routing is happening, and other components may be placed in somewhere else. So your critical path may be different, and like your delay is not actually calibrated. So it is very slower. I mean, the Fmax what you can achieve, that is limited. Okay, but there is disadvantage with the hard IPs also. I mean, like when I say that like hard IP, uh, what will happen is like you bought one IP with like ARM core, right? So let's say like you are not utilizing that part of the ARM core itself. I mean, the cost will be high, and the combination of the hard IPs, right? It has to be carefully chosen. Like usually now, if you see Zinc SoCs, so we will have like hardcore ARM SoC, we will have hardcore PCIe core, Ethernet cores, whenever actually this combination of these hard IPs, right? Basically, every hard IP is going to add like some contribution towards cost and size of the chip, right? So I mean, we cannot put everything as a hard IP, right? Like, I mean, one best example is nowadays, like we get something called RFS from Xilinx or AMD. So that particular IC is designed for your RF application or 5G application, wireless communication. So they have like lot of hard IPs in terms of DPD, digital up converter, DUC, DDC, right? Like up converters and like some kind of, I think they have turbo decoders, encoders. So these are all hard IPs. Basically, that chip is specialized for the application. So I mean, whenever you have more hard IPs, it will become like a ASIC itself. So your flexibility, like what we call configurability, right? That keeps reduced. So I mean, most of the things are fixed. So it will almost be similar to DS, right? So that is one thing we have to keep in mind. So few of the things like I mean comparison I have kept so soft IP usually it will be delivered as RTL code and need not be I mean basically encrypted packages they'll be giving. Firm IP basically they'll be giving netlist level and hard IP even GDS level and one thing many a cases like I mean this is like in terms of I can say uh, your ASIC design point of view. But like in FPGA point of view, this hard IP is already synthesized. It's already present in the FPGA itself. Okay. So like soft IP is moderate performance and hard IP is very high speed, right? Especially these hard IPs, as I was mentioning, like PCI, DDR, even ARM4, right? So all are like hard IPs. Whereas like your microblade kind of thing, right? And all, I mean, I'll be showing various soft IPs, maybe one or two examples we will take in the session. So these soft IPs basically you can instantiate in your design, you can utilize. But again, provided like the license is available. Let's say like you are using LTE FPGA, or you are using Viterbi decoder. These are licensed type. You have to pay some amount to for the license amount to Xilinx or like let's say whoever the vendor is. Yesterday I was showing you that like, there are various third-party vendors who design this. Mobile Highway, Mistral. So these people design this site, right? And like this is a collaboration thing. When I was in Samsung, we used to buy from the Cadence, Broadcom, like these all companies like collaborate each other and build. I mean, like few people will be good at something and few people will be good at. So when we collaborate and get various IPs, we can build a system. The memory wise, like some companies will be good at RF wise, analog devices. So that way like we have to collaborate and so everything like one company will not be expertise. So especially this IPs helps in collaboration in terms of companies and collaboration within the teams, right? So in terms of research, so one is actually soft IP, what I mentioned is the microblades. So you can actually I'll just show you that how to integrate this microblade. uh, if you open the block design, yesterday we saw that like how we can actually create a block design for the hard, that is a zinc cassette, right? Same way, let me create one block design. I'll just show you like how we can add the soft type. So yesterday, what I had shown that processor was already present in. Okay, now what I am adding that is not present in the present as a hard IP, right? So I'll show you the resource difference, how much resource difference we will get between a previous scenario and current scenario. Now, in the previous case, if you see yesterday what we had synthesized, so in that you can see like after synthesis, only one LUT and 32 flip-flop it took for the simple counter logic, right? Now, maybe with the same counter logic, I will add the microblade. So you can see the resource difference, how much it is taking, right? So because this processor is consuming your flip-flop and lookup table, okay? So I'll just show you like how you can add or like how you can integrate this microblaze processor. So you have to go to the create block design. Then here you can search microblaze. You can see various versions of microblaze is available. So you have microblaze is the processor and you have MCS. MCS is a controller. Let's say like you want to build one small controller inside. So yesterday I was telling you the trade-off also, right? You can say that like I mean now why do I need controller inside the FPGA? FPGA can perform all the operation, right? But again the resource matter, right? I mean, so let's say like now I want to build SPA I2C and like 6-7 interface, okay? And these are all for the peripherals which are very low speed applications, okay? So all these 7 interface I can fit as a software code inside the microcontroller or microprocessor what I implement in FPGA. And this microcontroller as a master, it can control all the peripherals. But whereas if I try to implement RTL for all these 5 interfaces, so it is going to consume that much of LUT, right? That many resources and that much time for development of these IPs and like interfacing integration. So always there is a thin line between like deciding whether I have to put this particular application on the software side or this particular application on the hardware. Okay. So any FPGA system you consider, there will be some part which we have to put into software. Okay. Uh, One example what I can give you uh, that was actually regarding like one of the application what I was working on. So I'll just show you that. Like I mean, maybe not completely because of the confidentiality. I'll just show you that like one of the system what I was working, how that is divided into software and hardware. Okay, just quickly let me put that system so that you'll get a brief idea about. So we were working on simple. I mean, that is actually for one of the drone communication application. So and that too, like it was a simple CDM application. Uh, Usually, you know that like in PPSK, if I consider, so I will have a data source and whatever the data I get. So initially, I perform some kind of FEC, and then there will be some modulation. You know that like in after FEC, usually we convert that code into NRG and then we multiply with sinusoidal signal and then we pass into that. Okay. So this is very simple, simplified thing. I haven't like gone detail. Uh, and also whatever FEC data is there. So here I also will have some kind of CDMA spreading. You know that CDMA is nothing but like we basically multiply each bit with the chips, right? So here we will have gold code generator. I mean, like we say pseudo random PN sequence generator based on gold code. So sinusoidal signal usually I generate using DDSI. Okay. DDS is one of the IP, direct digital synthesizer IP. From that I will generate. Now this data usually we used to get from if you are familiar with defense application. So there is an interface called MIL1553B interface, like just like a UART interface, but like which is like more secured communication kind of thing, and like error wise it will be like very less in case of that. MIL1553B. It's more than interface. It is actually like voltage levels and like error correction capabilities. It is good. So now here, right? This is one FPGA system, but in this system, like usually, let's say like this is going to some critical airborne application. So in this, I'll have like temperature sensors, I will have some kind of current sensor, voltage sensor. I will be also having some kind of uh, this one to say uh, uh, like say that gravity like accelerometers. Right? So all these sensors will be there, like temperature sensor. I will have current sensors because I mean this system alone, it's not just a transmitter or receiver, right? And let's say this DAC also, I need to configure through SPI. Like there will be various configurations. So I need to configure through SPI, and I need to configure this current sensor using I2C, let's say. And let's say this temperature sensor I have to configure through SPI. Okay. And I will also have clock. Uh, so this clock also, by default, this clock will not be coming. So I may be like configuring this clock through. I need to configure this clock frequency, right? So I'll be configuring through some SPI. So this is the scenario. Okay. Now the data again, it may be coming from some, like let's say like it is a drone communication. So you will have some network IP, let's say like Ethernet or anything. I will say like from that, it is coming to uh, okay. So we have chosen this MIL 153. No need. This, let's say like this whole thing is sitting in the drone. Okay, drone side. So let's not consider this network side. So through MIL 1553B, I'm getting uh, real time some GPS location, all these aspects. I'm getting telemetry data. Okay, telemetry data. So now here I have to decide which part of this design will go to software side, which part will go to the hardware. Can you tell me which part I can put it into the software side and which part I can put it into the hardware side? So this is like initially I have to decide, right? Like what part. So this is the general architecture where system designers will give. I mean, this is the specification what we get. I mean, if you have seen the tender from ISRO or DRDO, so they'll be giving this kind of top level block diagram. So if you see the IDEX portal also, they'll be giving some kind of uh, this top level overview. So in this scenario, how we can actually split the architecture into uh, software, which has to go to the software and which has to go to the hardware. So here itself, can you identify certain things? Right. So this one thing is like data, right? So MIL 1553B. So like there will be a lot of configuration to the MIL 1553B. So that part I can say data decoding, because some operating system has to uh, run. So like that I'll put it into software. I can say microblaze, and whatever the DAC configuration, right? Initially, only one time I'll be configuring that DAC, right? What should be my data format? Like it will be various formats are there, right? Whether it is two's complement or whether it is like a QMN format. There will be depends on DAC. So we have to configure that. What is the input data format? Whether it is a signed format, unsigned format. So that DAC configuration I can put it into software. Then this temperature sensor, is it real time? No, right? I mean, like every 1 second also, if I implement that, I can put it into software, temperature sensor reading, and even current sensor. Basically, these current sensors are for your system level error detection. Let's say like internally due to temperature, some short circuits are there, or like a sudden spike in the current will happen, right? So immediately we have to go for shutdown mode. So these things I can put it into all the peripheral access, like this clock access, clock configurations. I was telling you that accelerometer or GPS, all these things I can put it into software side because that is not data critical thing. Data decoding or like I can say command line RT interface, right? I can put it in software side, but actual data what I'm getting, so I cannot put it into software side. It has to process at the higher speed because that impacts my throughput. So let's say FEC encoding, if I want to do like let's say like this is a sequential process, uh, one after the another if I'm doing. So like here like FEC encoding it itself it may take few clock cycles. So there is a variation in the clock. Right? Like say like when I say spreading, so if this is the data bit in BPSK, within this data bit itself, I will have 1024 pseudo random codes, right? Like that is the concept of CDMA, right? Like what we do, like in within the data, we will actually put a PN sequence and multiply, XOR it, so that this data looks random. That's why we make it pseudo random sequence. So that multiplication and all, if I perform in software side, that takes a lot of time because this, if this is like 9600 data rate, and if I want to multiply this with 1024 pseudo random code, right? So my effective data rate should be 9600 into 1020, right? So I'm multiplying the clock rate by 1024. This kind of implementation, it is not possible in the FP, not possible in the processor. Okay. So I had seen some legacy system, even like before this SOC, I mean, this Zinc SOC in around like 2014 it came. I mean, 2014, like 2014 or 2013, in that year it actually introduced by Silent, FPGA SOC. But before in the legacy designs, like in 2005 or 2006, I have seen these systems are built something like this. You had external DSPs, like Texas Instruments DSP. There are DSPs like Sitara, some TMS series used to get. I mean, so those DSP processors they used to put, and like Spartan or some FPGA, low end FPGA they used to put, and they used to interface using SerDes lane, high speed SerDes lane. These kind of interface used to be there. Okay, so but again, disadvantage is like it takes lot of space. These both are interfaced in the PCB, right? So separate ESP, separate FPGA, that takes lot of space. But now after introducing this SOC thing, so everything within FPGA, like DSP is also in FPGA, that is ARM processor. FPGA core also, PL side also, right? So even sinusoidal signal, we have to configure, right? Like DDS, let's say DDS signal. So we have to configure because uh, let's say like the frequencies at what carrier frequency you want to transmit. Like there is something called frequency tuning word FTW. So that we configure. Okay. So then multiplication and send it to DAC. So this is a parallel interface. So all these things we put it into FPGA. Whatever the configuration parts are there, right? That we put it into the processors, like temperature sensor, current sensor, clock, and DAC configuration. Everything we put into software, which is slower, okay, which works with the slower speed. So let me put microcontroller itself, MCS, here. So if you open this microblaze, you can see uh, basically it is giving you option to like choose your microcontroller configuration. You can build your own configuration microcontroller, right? So you can actually enable IO bus, enable trace bus. You can have UART, PTT, GPO, right? You can also choose GPI, interrupts. So you can configure your own and like you can whenever actually it is implementing on FPGA, you can choose like what could be your like synthesized strategy, whether it should be area optimized, performance optimized, right? So whether you want to enable UART, right? You can choose this configuration and what should be the memory size. So ideally, like whatever you keep it here, right? Like this configuration, that is consuming your FPGA resource itself. Okay, so that is why like you have to be careful when you are choosing this configuration. Whatever the configuration you need, only that you have to. Okay, so then you can run automation like basic clock reset. All these configurations will be generated. So these systems, right? Like yesterday, I was telling you that hardcore IPs like ARM, SoC, those things it is very difficult to simulate. But like this microblade system, like by putting a proper ELF files, right? So you can simulate this microblade. So that is like straightforward. See this clocking wizard actually generated. So you can just make this as external. You can say that like this is coming from the external source, from external pins. And whatever the IOs are there, right? Like let's say like this IOs you can connect to uh, some GPIOs where you can actually control the switches, all this. You can make it external and this space also you can make it external. So once this is done, just need to validate. So you can see validation is successful. And for this microblaze, you have to generate the wrapper. The wrapper is something like where you can interface this to your local RTL code. Let's say like you have external counter. So through this software code, you control some IO. Based on that IO condition, if you want to run the counter, so that you can actually generate. So here you can create STL wrapper. So you can see this device got instantiated in the top wrapper. So whatever the signals are there, so this trace is something like for your JTAG part, but like this clock you have to connect to the external clock, and this log is something like whether internal PLL, whether it is logged or not, show. And whatever the IO part is there, right? You can see somewhere the IO part is. Yes. So this you can interface to your local device. So that is the idea. Let me just synthesize. I mean, let me not put any logic as such. Just let synthesize this and like see how much resource it consumes. Let's focus only on the resource aspect. And ideally, when you want to actually generate the uh, software code for this, right? So what you have to do is you have to export. Here you have an option called export hardware. Okay, you have to export this whole hardware. So whatever the hardware HDF file is there, so that will be exported. And here in the tools, you have to launch VTSID. Okay, so VTSID is somewhere like you can write the software code for. Okay, since I mean like software side is not scope of us right now in this workshop, so I'm not discussing that part. Usually, like this software part, right? I mean, in larger organizations, what we do is there will be two teams, like one embedded team who will be taking care of all the software side, where we write actually embedded code as well software. So, like they'll be writing various embedded algorithms. So the hardware team will be mostly focusing on writing Verilog code, instantiating the IP, building the Vivado project. So once it is synthesis is done, so we can see how much resource it is consuming. So yesterday we had seen that, right? I mean, like it was not consuming any resource. Like ARM core, even though we had instantiated, it was a hard core, so it did not consume any resource. Now you can see that like this will be consuming some kind of block RAM resource. Okay. So I mean, meanwhile, let's continue our theoretical part. Let it synthesize so that like we can save some time. Okay. So usually when we want to actually uh, create our own IP, right? So what we usually do is we write a Verilog code, we simulate like that loop you already know, like we fix the error and we keep simulating. This is one loop, and then we can prepare a IP packaging. So there is a package like called Vivado IP package. So if you look into this tool, right, like let's say like you have one Verilog code. Uh, Let me say that like you have one counter. So here in the tools, you have option called create package and create new IP, package new IP, right? So you can create your own counter and package as IPs. Okay, so once you write a Verilog code and like you simulate it, if the IP is working fine, so then you can create IP package. Okay, so there is like various uh, encryptions options also, but like let me just show you that like how you can create your own IP package, like this microblaze thing complete. So after that, I'll show you like how you can create your own IP package. So once that IP package is completed, so in the IP packages, you will get an option like whether you want to create a AXI based IP package or like simple uh, IO interface kind of IP package. So you can choose that option and you can create a IP package for that. So once that is done, you can just again that if, by instantiating that IP in your design, you can simulate that and test the IP. Okay, so then you can actually generate the final IP and publish IP code. So there is actually like for Altera, you have Altera IP stores, And same as Xilinx IP storage, that you have to register as a valid vendor with them, and you can publish that IP. Okay, so that Acronics also, they started with the IP business, and Synopsys also, it's a fabless company. So one thing you have to understand, I mean, whenever we talk about VLSI, we always think of fabrication, heavy investments, all these things. But VLSI is not only limited to fabrication of die, right? If you see companies like Synopsys, if you see the companies like Mobile, Cadence, largely ARM is the best example. They never fabricate. They don't have any fabrication facility. They just write the Verilog codes, they synthesize, and they sell it as IP. Okay, so I mean,
Sir, at
yeah,
this point, sir, can you say what may be the maybe future considering the design of IPs,
mhm,
considered only for this VLSI side, sir? What may be the future for the students, in what line we need to take? Because there may be, because fab and all, it is really costly.
correct.
So the design of IPs, maybe if you go for the Verilog, it may not give everything completely in terms of maybe timing. Really, if you look into the fabrication side, so
Correct.
how to go about it or something, because I felt this is the design of IPs. It's very important because at present we
Yes.
may not have anything from India side. We are borrowing, maybe number of IPs may be less. I
Yes.
so some.
Yes. Many IPs, especially like in your, we talk about lot talk about this artificial intelligence also, like CNN, convolutional neural network, like even language, like your neural this one, LLM models, right? So that also some acceleration may be required for this, right? I mean, now we talk about GPUs, like we are building indigenous. We lot talk about building our own GPUs, but when we say GPU, internally it consists of a lot of IPs, right? So we have to focus a lot on like developing these kind of IPs, like where it accelerates, especially your vector signal processing, like matrix multiplications, like complex matrix, and even 5G related things. Like in 5G also, you have a lot of opportunities, like to build your own IPs, signal processing, like even what to say, FEC based, Viterbi, up converters. My research, what I'm doing is like building various MIMO IPs. That like in 5G, we have a lot of IPs, but again we have to, like when we say that, like let's say like in India itself, one company is building one IP. If they are borrowing from someone, still we can compete. I mean, if we are able to build like power optimized IP, or in terms of area optimized IP, so still we can build those scenario. One thing what I suggest is like currently this vision, AI, and 5G. Okay, for some extent, we have a lot of scope in that. Like we have to identify one of the field, and we have to start designing various IPs around that. I mean, any research project what we build, right? So you have to think in terms of IP. Right now, in from my research team also, where I'm doing PhD. Whatever we are building, we are thinking in terms of like how I can make it as a commercial product and like sell it to someone. So in research also, what I recommend, like you just see that like commercial viability of, because uh, uh, that is actually like golden opportunity for us, right? Like especially in the research, like you'll be spending around 5 years. Each PhD student will be spending 5 years, and whatever the RTL or Verilog you develop, that should fit somewhere. I mean, you can sell to somewhere. Like, I mean, in terms of opportunities also, like what IP I can develop. Uh, One easy way is like now Indian government itself across all the PSU, like we say Navaratna PS, PL, BHL, DRDO, uh, Navy, all these guys, they actually started telling what are the problem statement. openly using their platforms like in edX and all. So you can see the certain problem statement and like you can start developing those ideas. So like last year we started one from the IDEX part itself, developing DVBS2 protocol. So so far like we are actually buying from either Israel or from somewhere. So this DVBS2, S2X, RCS, these are satellite communication protocols. So like you have to identify the opportunity, especially in communication and 5G, communication, 5G, vision, and AI. So a lot of opportunities. And Synopsys is one like extensively providing these. So there are like various other companies also. In India, we started. I mean, Fabless is like without investment, like I mean, again, like till RTL level, you need not have any investment. Like to convert GDS level also. Now you have open source tools, right? Like you have Yosis and like that open FPGA is one of the paths. That is where like you can build your own FPGA. And RTL to GDS open source flow is there. In NPTEL also one course is there. I think from triple IT, not which triple IT I don't remember. One of the triple IT launched the course in NPTEL on RTL to GDS. So that kind of things, if we are able to achieve, right? So in the IP level itself, we can make commercialize. So I mean, for the institutes, again, we did not go for the open source also. I think like most of the institutes here, you might have subscribed to that CIPIN program, right? So CIPIN center. So all synopsis, everything, all the high cost tools the government is giving.
Okay, sir.
Hope
Thank
I
you. Thank you.
answered. Yeah,
Yes,
yeah,
thank you, sir.
yeah, yeah. So synthesis is completed. Uh, okay. So see here one mistake what we usually do, right? So which I did now also. So in Vivado, right? Like whichever the multiple devices are there, you have to set which is the top model. Only that will be synthesized. So here what I did is like I actually synthesized yesterday's design. That's why you can see like one lookup table and 32 flip flop. So this one you have to set it as top. Whichever the design you want to synthesize, first you have to set as top. Okay. In the simulation also, people make that mistake. So they don't set it as top. Uh, they'll be keep simulating. So you'll not get the output. Main reason is like some other module might have top, right? So you have to like whichever the module you want to simulate, you have to set as top. Okay. So run synthesis. And one field what I think like you a lot of potential is there like where India is lagging on the memory controllers. No memory controllers are. If anyone interested, you can start work on that. Memory controllers now usually it is borrowed from a lot of memory controllers, DDR or like your flash memory, NAND flash, NOR flash, all this. So that also like it's a good research. Okay, if you're able to build memory controllers, there are many customers in India itself. Okay, so let it synthesize. See, this is one of the example for hard IP core. This is a PCI IP core, right? So hard IPs are physically embedded inside there. So you can see that like PCI transceiver. So usually PCI transceiver, when I talk about PCI transceiver, right? So it is actually SerDes lanes. So usually you will have uh, like differential signaling and like some elastic buffers and internally like high speed PLL is there. So this SerDes usually it operates at 1.5 gigabits per second. Higher speed, like PCI Express is running at very high speed, like up to we can go up to like I don't remember exact speed of this. So I had worked around 8 gigabits per second, like with the parallel lanes. So these things we cannot actually put it into FPGA also, right? So they actually hardcore, they build hardcore PCI IPs, so that like I mean only user interface, right? You can see here what they do is they embed this MAC layer, transaction layer, in certain cases transceiver layer they embed, and like this MAC layer, transaction layer, user layer, they make it soft. Okay, in certain scenario, what they do is like they keep all these things hard, and this they will give it EXI. So you just need to configure that hard by giving that what is the configuration, and you'll be keep getting the data using EXI. So that is one thing. Okay. So ideally, the maximum performance and minimal power usage. That is the main reason why we go for hard. Okay. And there are like various popular IPs from the Xilinx. Okay, so we'll go one by one. One of the thing I'm already building, microblades, right? So like we have block RAM, clock manager. So that is very important, like MMCM. So in all your designs, you will be dealing with multiple, right? So whenever in FPGA we say that like I want to generate different clock, people directly go and write very low code. Like let's say like I want to convert from 50 mega to 25 megahertz. They start writing the divider logic. So that is not the right approach. So we have to go for PLL for the stable flow. Because when you actually use this lookup table, one thing I had told you that like it is not going to utilize dedicated clock path. Another disadvantage is like you don't know like logical delays. Right? Basically, that impacts your duty cycle, and all. So you will not be getting stable clock. So you have to go for MMCM. Okay. So there is one question between AXI IP and IOIP, which is better. How we will choose? Yeah. So if your logic is within FPGA, right? Then it is recommended to go for IOIP. Okay, let's say like you are writing your own custom logic. But let's say you are interfacing this IP with some processor, ARM processor or like this microblaze. So usually this will be address map, or like let's say like your IP you have to interface to some external streaming sensor. Like you have like let's say uh, let me give you an example so that like you'll be clear. With respect to example, let's discuss. So you know that in the EXI, we have these data sequences, right? Like data, and if it is memory mapped, you will have address. But if it is streaming, you will have data and clock, EXI clock, and you will have some TLAS that is for TLAS and frame start. All these things will be there in EXI, right? So in one of the application I was telling you about like DVBS to IP what we are building. So like ideally, let's say like you have to get a real-time data from camera. Okay. So this camera, like let's say it is a PSI interface. Okay. So from camera, you keep getting the stream of data. Okay. So this stream of data, I have to store it in FIFO. Okay. So this camera data, ideally the operation what I had to perform is like first I have to do H264, then I have to encode into DVB-S2 for like this camera is actually mounted on microsatellite. Okay, so this like ideally it is sensing what are the earth parameters are there, temperature or geological survey. This camera you can think like some application. Because of confidentiality, I may not be able to reveal where exactly I'm using it. So some application getting the data, I have to do H264 encoding, and through DVBS2, I have to transmit to ground station. And So this camera, right? Like whatever the data I get from CSI interface, I will have some frame reference that I can say frame last, T last. So whatever the operation I perform, like here in H264, in H264 also I can say like around 5 to 6 stages are there. In DVBS2 also 5 to 6 stages are there, like data scrambling, data modulation, FEC encoding, right? All these stages are there. Like again, you have to add DB header, like for like as per DVBS2 standard, around 5 to 6 stages are there. Everywhere, like this FIFO, like you cannot read the data until next stage processing is complete, right? So it is like there should be some acknowledgement from the next module. Based on that, this module can send new frame data, right? Acknowledgement and response kind of logics are there everywhere, like sequence, it's series of operations, right? Like block by block. So in that scenario, I will go for AX where like each block has to communicate, or like one master has to come and control all other multiple slaves, right? So where these kind of scenarios are there, generally I prefer take center. But whereas like there is each modules are independent. Like one module is not dependent on, let's say like clock configuration. Once I configure the clock, like I have PLL. Let's say I configure frequency. After configuration of the frequency, this PLL start giving the clock. Then I need not like configure at all, right? It is one time. So in this scenario, you can go for simple IO kind of interface where like multiple acknowledgement or control is not. So that kind of application we go for PLL. Hope I answered your question. So it is still running. Okay, so by the time it completes, so I'll also try to explain you another concept. So in FPGA, we have seen like architecture from 2 3 days, right? So what are the options available for me to store the data? What are the different options available for me to store the data in FPGA?
BRAMs are there, sir.
Correct. One is block RAM. Any other thing? Any other option?
Bitwise D flip-flops are there.
Yeah, flip flops are there. I mean, like it's again like for storing the data, I cannot use. I mean, as a registers, I can use. I can registers, right?
Bitwise
As a
only,
register.
bitwise.
Yes, yes, registers. Then
Um, Sometimes prom might be there for transferring the bit file in case we are going for maybe on dynamic configuration. There may be
okay,
read-only
okay,
memories.
yeah. So yeah, read-only memory is a PROM again, like somewhere in the RAM itself, it is actually not. Right? So read-only is not possible. Yeah, I mean, there are like FPGA types, like usually like in Xilinx FPGAs are SRAM based. So fuse-based FPGA and like read-only FPGAs, all this will come. I mean, especially for SATCOM application. But in our application, like we'll have VRAM, register, and even lookup table also can be used as memory. Lookup table is also one
Yes,
memory.
yes. Lookup
So
table.
we call it as distributed block, distributed DVRAM, right? Distributed block RAM. So if you see the template, I'll show you that also. Like there is an option called distributed block RAM where you can store using LUT itself. So this is within FPGA. This I can say within FPGA. But given one FPGA, I have limited memory, right? Like now we talk about video processing or high speed processing like or LLMs, but our whatever the memory available inside the FPGA like block RAM, registers, lookup table, that may not be sufficient. Let me show you that exactly how much memory available. So I'll give you an idea like how one FPGA when you choose how the resource table looks like. Yesterday I was telling you like to look into the 7 series product guide, right? So let me open that PDF itself. So this is actually 7 series FPGA. You can see Spartan, Arctic, Skintex, Vertex. So in this PDF, if you look into various part number, it is basically part numbers are categorized based on the resource. So here, if you see this part number, like block RAM, total block RAM available in kilobits, like maybe 4 KB, 11,700 kilobits. Maximum 34,380 kilobits, right? So whenever we talk about image processing or LLM, it is a gigabits of data. So if like for the smaller chunk of data, I can still go for what to say block RAM, LUT, and register based. But when the memory size keeps increasing, so then I can start interfacing external interface, uh, external memory. And the usual memory what I use is DDR. This is processing memory. Okay, like let's say like stream of image is coming, so I have to temporarily store that image somewhere, then process inside the FPGA and send it to some other like maybe through network or I have to store somewhere permanently. So in that scenario I use DDR. But let's say like I have one drone application which will be keep monitoring real time data, and it has to store, you know, that FPGA DDR, all these things are volatile, right? So as soon as reboots, all the data is erased, right? So in that scenario I will go for flash memory. Flash memory, this is for even like for storing the permanent configuration, right? So like certain settings, I was telling you an application of communication where I have to store the gold code, I have to store like mil 1553b, or like I have to store the encryption keys, right? So for all these application we will be using flash. It is permanent in nature. Okay, and even usually we measure the drone in run like flight time, right? Like how long it flies, depending on the battery capacity. So one of the project what we are doing is like it is basically it flies. So that whole duration, like let's say 1 hour, so that data should be stored in the flash. So we usually go for NAND flash, NOR flash. So that is one of the applications. So this categorization, like choosing the memory, right? So fast, which is the fastest one? So LUT and register, that is the nearest, right? That is the fastest memory item. Okay, and this block RAM is little slower, but faster than DDR. Okay, DDR is lowest, and flash is like further slow. But again, this between this VRAM and LUT, now in my micro this one what ultra scale FPGA, we also have URAM, ultra RAM feature. This is very high scale. compared to your block RAM, this is further faster. Okay, but now there are like limitations, like you cannot like always use lookup table as an, okay, because it is consuming precious logic elements. But still, why do we use lookup table as an, there is one reason. So block RAMs are available as block. Okay, so let's say like this block RAM in Xilinx, it is available as 36 kilo block, 36 kilobit block. Okay, so one block size is 36 kilobits, and this is capable of using half block also. I can use half block. I can say like I will be using only 18. This is permittable. Less than 18K I cannot use. Let's say you have 256 bit of data, okay, encryption data. If you try to store it in this block RAM, minimum it is taking 18. Less than 18K it is not possible. Okay, so in this scenario, what I'll do, I'll use lookup table as memory, LUT as memory. Okay, I'll map into LUT instead of block, because in this only 256 bits is used. Rest of around 17 point some bits, it is used unused, right? It is waste. So for whenever you are designing FPGA, optimal resource utilization is very important. You might not notice these things when you are actually dealing with smaller designs, but as the design grows, when the design becomes complex, so then all this optimization will start coming into picture. Okay, so I mean, like one of the scenario where like I was designing one filter, CIC filters. So like almost 3 months we worked on like optimizing that CIC filter, because whole design was not fitting within FPGA, right? So every gate level analysis we were doing, where we can actually optimally map the whole thing, right? So uh, this is how we have to decide whether you want to map into lookup table or whether you want to map into block RAM. Whenever you are choosing the memory itself, you have option to choose whether it is a distributed. So usually mapping your memory into lookup table, we call it as distributed block RAM. Okay, distributed block, because that block RAM is distributed across lookup table. Correct? So still it is running synthesis. Usually this microblaze, initially this design, right, it takes a lot of time to synthesize. Design clock is synthesized, it's actually synthesizing the memory, the microblaze core. Okay, so let it synthesize. So uh,
Sir, actually, how configuration takes place, sir? We configuring the FPGA itself when we bit file, end file, when we are downloading, how it is going to configure?
yeah, so ideally, like each bit, right? So irrespective of your whole uh, FPGA, like I mean, like let's say like you have one AND gate, or let's say like complete bit file, which is all the lookup tables are present. So ideally, what it does is like each bits, right? So it is going to map. I mean, like whenever you generate the bit stream, right? So for each XY coordinate, right, each xy coordinate, it is going to generate like what it should be there. So that is where like compression of the bit file is possible. But even after compression, so when in the core, right, what is going to happen is like it is decompressing, and it is going to identify each bits. So like in like usually how we configure, like either through JTAG. JTAG is the one way how we configure, or we will remotely upgrading, like using some UART interface, like where actually like some processor configures it, or like basically what we do, like ideally this the architecture will be like in flash we'll be storing the bit file. So one way is like when we say remote upgradation, so the flash upgradation we should, that is one thing. But inside the FPGA, that is dynamic configuration of this thing. So ideally, each bit, right, through JTAG or like quad SPI core, so bit by bit it is going to configure. Every bit will be reconfigured. But in case of partial reconfiguration, usually like we use some P block based thing, and we say that like this is the partition what we have to configure, like this part of the design we have to configure, right? So then what it is going to happen is like without powering down other logic, right? So only that part will be configured. So that is like we generate partial reconfiguration bit files, right? So that way.
So each bit that is required for particular maybe switch, it will have some address then maybe. Because it
It
has
is
to go
not.
to that particular switch only, it should be. In case if I am taking the LUT, maybe it has transistors only, maybe 6 transistor, 5
No, no,
transistor.
no.
Huh?
No, actually, each logic block, right? It has a coordinates. So it will
That
say
is
that
the address
X12,
only
Y13.
then.
Yeah, yeah. I mean, like when we
Ah.
say sequence of data should go, so
Hmm.
each each switching matrix and each what we say lookup table, each uh, like say like even D flip flop, there is a mux, right? So for mux also there is one memory bit. So for
Yes.
each thing, there is a sequence like we say vector programming SVF file. I mean, if you remember in older FPGAs, we used to generate SVF file. So that vector file in particular sequence when we program, right? So that is going and sitting. So I mean, ideally, like storing an address in that particular bit file is not feasible because like you have millions of bits. So in a particular sequence, it has to program. So that way, like internally, it will control. Okay,
Oh,
this is first bit,
oh,
second bit, third bit, fourth bit, right? So when we go for partial reconfiguration, it will have one reference. So from reference onwards, that sequence again it will start. Like till here to here, it has to configure. So that way it will. So when we say partial reconfiguration, so one part of the FPGA we are configuring, right? It is not that like one LUT here and another LUT here. It is not that. So you mark the P block and that P block you reconfigure.
okay, okay. Thank you.
So block by block only is possible. So because from I mean there will be some offset and from there it will be keep reprogrammed. So there is one question for image processing. At least how many DSP blocks are required? So again, Parth, I mean, this is very generalized question. So this is something like depends on your implementation and uh, what is the application. So image processing, it can be like simple RGB to gray conversion also, or it can be like high-end facial recognition or CNN applications, right? So depending on your application, for what purpose you are using, according to that, you have to choose the DSP, right? So ideally, what you have to do, like before buying FPGA, right? So first we have to synthesize. I mean, during synthesis, you need not buy any FPGA, right? Then you have to go to this table and choose. Like let's say like your device is taking 1000 DSP, right? So then this is ruled out. This device will not support, and till here, this device it doesn't support. You have to go for 1440 device, right? Now let's say like 1440 DSP slices are fine, but I need 80,000 slides. 1440 fine. So it requires it is actually having only 55,000 slides. So then 80,000 none of these devices are support. So Kintex is ruled out. Then what you do, you go to Vertex. So in Vertex, it's starting from 91,000. They are actually going right. So you can see Vertex 7. So the slice is 97,000, 91,000. So then I'll choose Vertex SP with 1260 DSP. Now someone says that like okay 1260 and like I mean 80,000 1200 is fine. I need 2000 IOs, so higher IOs. So let's say like 600 IOs. Okay, 600 single ended. So this supports the 850 supports. uh, but again like this is 850. Again 250 extra IOs are there, power may be more. But here optimal I have to go. So you can see here like 600 IOs. So 2000 DSP slice. I have 86,000 logic slice. So I can go with this, right? And now you have to also see that like whether it supports certain speed, right? So speed rates are nothing but like for commercial industrial defense, uh, automotive, various speed grades are. Okay, so you have to see like what is the temperature range. So for each speed grade, right, -1 to -2, so temperature ranges are. So let's say for commercial application, right? So 0 to 40 degrees is fine, like 0 to 40 degree or 0 to 70 degrees is fine. But let's say like I'm going for defense application. So in that case, usually they recommend like a -40 degree to up to 113 degrees, because let's say I'm using a particular application for missile purpose. So you know that like this missile may store in like some Kashmir or somewhere else. So that temperature is very low there, like -degree, -10 degree, -5 degrees Celsius. So initially it should power on. So for that itself, like your FPGA should support. And once the mission is fired, it goes up to like 100 plus degree. Your devices will going 100 plus degree. So that whole profile should support. So we usually this kind of application, what we do is like we do combined CAT test, combined attitude, longitude, humidity, temperature. One more is there, CAT, combined attitude, temperature, humidity, and latitude. I guess something like CAT test we say. So that test we do. So there, what we do is like we actually vary the humidity. We vary because like what happens like this FPGA should work in the saline environment. So you know that like if you go to like Bangalore or some places, there is no saline environment. So your FPGA boards will not. I mean, FPGA hardware will not impact so much. But let's say like in my area where I stay, you can see my FPGA board itself. There is like lot of rest on top of this thing, because like I stay in coastal region. So like these kind of scenarios we have to take care. I mean like especially like if you are deploying your device in Navy and such application, lot of saline environment will be there. So your device will start degrading. I mean, whatever the components are there, right? So usually we do something called saline test. Like we keep in the saline chamber for like maybe 2 to 3 weeks, and we see that like how that actually your device uh, responded for that. So even like one of the tests what we used to do is like we take the temperature. Like there will be temperature chambers available. Like there is in-space laboratory, and in Bangalore there is a laboratory called Tarang from Wipro, and Tata Advanced System is there where they do this kind of tests. So we can take this FPGA board inside that chamber where we can bring the temperature to -40 degrees. We will be powering off the device. Okay, so what happens is like if your device is powered on, so it will be generating some heat, right? Like FPGA itself is generating heat. So because of that heat, so even if you take -40 degree, surface temperature of the device will be like maybe 20 degree, 30 degree. So still your FPGA will power on. So what we will do, like we will switch off the device. We take the temperature to -30 degree, -40 degree. Then we try to power on. So still it should power on, because let's say like someone take the device to Kashmir or like Himachal or somewhere where the temperature is negative, right? So your device is off, and then when they power on, so your device should be powering, right? So that kind of testing we have to do proper. And some case what we will do, like we will take the temperature completely to 113, 114 degrees Celsius. There we will power it on. Okay. So there will be definitely like there will be some variation. So that buffer we will be giving. So whenever the temperature goes to 115, 116 degrees Celsius, because of the temperature, your clock will be slightly drifting. Like let's say like 100 degrees Celsius, 100 megahertz. So it will start showing 100.1 megahertz or 99.99. So still your design should be susceptible to that kind of uh, variation in the uh, temperature and clock. Okay, so various scenarios we have to take care. I mean, like I mean, like as a design, right? Like I mean, uh, especially the system design is very interesting thing. I mean, like if you get opportunity to work as a system, right? It will be like very nice. So I mean that one good thing is like about like in my initial days of my career, like I feel like around 4 to 5 years I worked on like completely system design. And my master's is also from MS Ramaya, is on electronic system design. So there is a lot of things to consider as actually like when you deal as systems. Like, and you will get to know like end to end, like from the customer giving like specification till you deploy it in the mission, right? So that whole cycle you will get to understand. That is the good thing about systems. Yes, so it's synthesized. So now, like you can see, one strange thing happened here, right? So like everything, it actually zero. It is saying it consumed zero. And if you open synthesis design, you will see no design at all, right? So yesterday I was telling you one concept there, like the closed circuit, right? Like I mean, in FPGA it always expects like input to output closed systems, right? So now let me just show you that schematic. So that explains whatever the thing yesterday I was telling you. So so one thing like in FPGA designs, right? Like whenever like you are using this Vivodo tool, make sure that like this is installed in server PCs, which has like at least 32 GB of memory. So else like it will be very slow. Right now, like since I'm using this Zoom and like browsers, multiple devices, it is taking a lot of time. I mean, even my PC has like 32 GB of RAM, so it takes a lot of RAM. And there is one question in the chat that like when to use commercial and industrial. So commercial temperature is like general like normal users what we use, right? So I mean at the max, like what commercial temperature is like who customers will be using. Like we will be going at the max 40 degree. I mean depends on like which area you are there, right? And at the minimum you might be like dealing with minus 10 degree. Let's say like Kashmir worst scenario, like it may go up to minus 10, like somewhere in the Everest or something. But in industrial cases, so which is deployed in the industrial machinery, let's say like uh, some manufacturing hub or some manufacturing plant, right? So in that scenario, your temperature may start from minus 10, the same, like starting point will be minus 10 itself. Higher end, it may go up to like 70 degree, like 80 degree max, right? So defense applications is the worst case. Okay, defense and SATCOM almost come similar, but in SATCOM, actually, like we will also have to consider the radiation tolerance because along with the temperature, in the space we have the lot of radiation. So our FPGAs, right? So what happens is like as you understand, like every bit matters in FPGA. Let's say you have one complete FPGA, in that one bit is corrupted, whole circuitry will spoil, right? So there they use some techniques called scrubbing mechanism. So they keep refreshing this switch every time. Also they use some parallel mechanism. So let's say like one chain is failed, so they will go for another chain. There is also, I mean, especially this for satellite application, we use micro chip-based FPGA. So they have something called polar fire FPGA. So they have this radiation tolerance. This Xilinx also recently they released. They're saying one of the FPGA is radiation tolerant. So they support that. So we have to go for radiation tolerance. So choosing the right FPGA is very important for particular application. Okay. So here, right, basically, this microblaze, like since like as I was saying, so like this is a black box, right? So they are actually like, I mean, and one more thing here, why it is showing zero is because like you haven't connected any of the IOs, right? Like I mean, it is like open-ended, right? So if you go to the top, this is kind of floating. You have a design, so you haven't connected anywhere, right? So that is where, like, until you have a closed circuit, like you have one input, you have some logic gates, and you connect that into output. So then only this will be consuming some resource element, right? But here, microblaze, I have instantiated this IC, like I mean, as a processor, but it is just floating, right? I mean, it is not connected anywhere. So in the next stage, what it will do, I mean, if you implement this design, right, whole design will be trimmed off. So always in FPGA, it is valid design only when you are actually connecting the thing. Let's say you designed one counter, you don't connect to any IO, and you just put it into FPGA and run. So it is not going to synthesize. It will trim off and it will show zero resource. It will not run. Okay, because always it expects there is a closed circuit, right? Because we are building the circuitry, right? I mean, let's say like I'm using one lookup table and there is no, I mean, input to that lookup table, no output to that lookup table. Even if I map that configuration bit, it is of no use, no meaning. So only valid meaning signals will be mapped into FPGA. That is very important. I mean, many a time, uh, especially this mistake, what people will do is our R&D project, right? Like you design one IP, let's say. Uh, one of my uh, PhD uh, research, I'm actually designing this matrix decomposition algorithm for MIMO. So in that, like what we actually do is like, I mean, that is the independent IPs. I mean, like if you map into IOs, so that takes thousands of pins, right? Like I mean, 8-bit, 8-bit, and I'm trying to decompose 1024 cross 1024 matrix. So if I just put that matrix multiplication algorithm inside FPGA, and if I synthesize, it will just trim off. I mean, it doesn't, it there is no significance of it at all, right? Putting it FPGA. Many a time, like we do that mistake. We'll try to synthesize and see that like how much resource it is utilized. That is not the right way. What you have to do, like whatever the design you have, right? So you have to boil down to few inputs, like one or two inputs. Let's say like some clock, and whatever the impact of that is there, right? You write it to some block RAM, and that block RAM, based on that block RAM result, you make sure that you are connecting some signal, like high or low signal to output. Then you can synthesize. Or there is another way in synthesis called standalone module synthesis. Okay. There is actually, if you go to the settings of this project manager, so there is an option called standalone synthesis. So in that scenario, it will not synthesize for particular device. Okay. As the IP, it will synthesize and tell you the resource utilization. You have to do that standalone synthesis. Okay, else it will show the zero resource. And many a times, like I've seen that like people making mistake that like that resource estimation itself they'll put it in record it in the journal. So that is not correct. I mean, like if you want to have accurate resource estimation, you have to go for a standalone synthesis. So if you go to the synthesis setting, so here you can actually give various settings. Okay, so resource sharing, whether you want to flatten the hierarchy. So for each things you have meaning like various meanings, so please go through this. So here there is actually one constraint available. You can just check it in synthesis. So there is one document from Xilinx synthesis guide. Okay, so you can just go through that. So there is an constraint like what you can put like standalone synthesis. So if you put that right, so it is going to synthesize standalone. Okay, and many a time in industry what we do is uh, we write various TCL scripts like before synthesis what should happen, after synthesis what should happen, right? So here let's say like there is lot of warnings. Okay, and we have written automated script where it will like post synthesis it will just analyze that, like is there any error, is there any issues in the design, right? So that TCL script automatically verifies, or else like what will happen is like every time you synthesize, there will be thousands of errors. So you have to analyze each error in detail. So that is not correct, right? And one more thing, whenever you see the timing violation, so you can go for different strategies. Okay, so you can see we word synthesis default strategy test chosen, right? So here you can choose various strategies of synthesis available, whether area optimized you want, whether you want performance optimization, whether you want lesser runtime. Okay, because like you see now, like it is taking a lot of time to synthesize, where your performance and area is not important and you want quick run. So you can go for runtime synthesis. Okay, runtime optimization. So these optimizations also choosing is very important. Okay. So I was talking about compression, right? Like you can see here, whether you want a raw bit file, you want a mask bit file, you want bin file, right? You want a logic location file. Whether like here, right? So you can actually add like whether you want if you want any encryptions, like you can usually people will encrypt your bit files because I mean, see, in using bit file, there are like I heard that like they will reverse engineer like netlist. So that thing also they will do. Like your when you deploy your product in the field, you don't have control of your bit file, right? What you have programmed algorithms and all. Reverse engineering is very tedious, but at least you think of this. So your bit file will be in Flash. So they will read back and they can keep on uh, like manufacturing similar device with a similar bit file, right? So that kind of copying they can do. Okay, so like I have seen that like locally few electricians, right? So like especially for LCD TVs and all, I have seen people will be doing that. They know that like some flash files will be there in the uh, EEPROM. Okay, so what they do, like I mean, that flash is ideally that will be they'll be getting from Videocon or some companies, but they will be having copier file and copier device. They just keep the IC, copy the flash value to another blank flash, and they sell it to someone. So that kind of thing will happen. So you have to encrypt your thing so that like that encryption key somewhere it should be within like somewhere like in some EEPROM or somewhere. So that kind of encryption is also has to be done, and compression. So your flash has a limited memory, right? So that compressing that flash is also very important. So this bit file you have to like cannot load directly as is raw bits. You have to compress the bit file and load it into a flash. Okay, this is actually like this doesn't make any difference if you are directly debugging using JTAG. But let's say you are deploying this into product, you have to actually store this bit file somewhere, right? Every time it boots up from flash. Every time you cannot connect the JTAG and deploy the product. So you'll be storing it in some memory file. So in this particular board, you can see here there is SD card. Okay? So you can see this, there is one SD card. Yeah, here there is actually SD card. So in this FreeSOC, actually the SD card is the flash. where I can store the bin file and I can reboot every time. Okay. The same way, like you have to choose what is the storage device. Okay. So regarding block RAM, so if you have to go to IP catalog, if you want to add block RAM, so you can see here BRAM. So here you have to search BRAM. So you can see AXI BRAM controller and block memory generator. So this is the one what we have to add. So here, like here also you have option like whether you want AXI or native. So if you want AXI, you can connect to like any AXI devices, or native is something like very basic interfaces, like you have address, clock, D in, D out, enable, and write enable. Okay. So and in the block RAM also you have various options like single port RAM, where like if you choose the single port RAM, right, you have like address, D in, D out, and write enable. So only one port. Read and write should happen in the same port. Okay. So for the slower interfaces and all, this is fine. Okay. And if you want dual port RAM, where in one of the side you'll be keep writing, like port A will be, you can see D in A, write enable A, address A, clock. Port B is mostly read. So in the read port A, you'll be writing, port B will be reading. So this is also used for your CDC application. You can see clock A and clock B is different. So you can keep writing in one clock, let's say like 100 megahertz. You can read at 50 megahertz. But again, like there will be overflow. You have to control using some technology. Okay. So other scenario is true dual port RAM. This is somewhere like you can read and write both the sides. So in the true dual port RAM, you can see here address, write enable A, D in A, D out A, everything is there, right? Read port, write port, everything is there. Here also port B also can write. D in A also is there. D in B also is there. D out B also. Both the side you can read and write. This also can be used for uh, CDC. And again, like if you want common clock, you can click common clock. So what happens is like both read and write will become same clock. You can see now clock A. In the port B, there won't be clock. Even though they are showing clock, but it is a common clock. I mean, internally it will be shown. Okay. So, and ROM. Let's say like you want to store any encryption value, or you want to store one sinusoidal signal generators, right? So or you want to store some kernels, especially for CNN application. So that time you have to use ROM. You have to predefine the value, right? You just there is no write option, only read option. But you may ask like how I can initialize. So if you go to the other option, there is an initialization option, load init file. So you can load a standard format called COE file. So in the COE file, you can store all the data. So in the bit file itself, that value will be embedded. Okay. So this way you can initialize the whole data using COE file. Okay. So COE file, there is a standard template. Nowadays, like if you generate, I mean, a lot of Python scripts are available online. So if you feed the text file, right, so it will generate the COE file, and so it can be anything like bin file, hexa, octa, right? Any file it can be generated. And here you can choose the width and depth also. Like let's say like port A, how much width it should be there, depth it should be there. And one important thing, let's say like I was telling you concept of minimum size, right? Let's say like in port A, single port RAM, port A option. Width is 16 bit. Okay. So read width also let it be same. Depth, let me say 10. Okay. So how many, what is the total memory size now? I said like width is 16, depth is 10. So what is the memory size now? How much memory required for this? Write width is 16, read width is 16, width is 16, depth is 16, 10. How many bits data? No, it is data depth. It is not address depth. It is data depth. 16 bit width, 10 bit, 10. It is not 10 bit depth. It is 10, actually 10 locations. So address width is 5 actually. If you see here, address width is, I think, much 4, right? So 10 I can actually represent with 4 bit, like up to 16. So how much location I need? 16 into 10, right? 160 bits. So 160 bits are required. So if you see the summary, still it is taking 18K block, and this is the disadvantage. So now, like if I change this into 100 also, now 1600 bits, right? So my memory size will be still, in summary, if you go, memory size will be still 18K, right? Now if I change this into, uh, okay, let me change this into 20 and 20,000 data, like depth I'll keep it 1000. Okay. So now it is 20,000 data. In summary, if I go, now it will take 136K RAM. Previously it was taking 118K RAM. Now it is taking 136K RAM. Okay. Read clock cycle, it will take 2 clock cycle latency. In the sense, if I give the address, right, after 2 clock cycle, it is going to give me output. Okay. So, but that is because I have added one register at the output. Okay. Especially to meet the timing. So, like usually if you remove the primitive output register, okay, we give the clock at 1 clock cycle. In the very next clock cycle, you're going to get that. Okay. So, but this always you keep it enabled just to meet the timing, because timing is also issue, right? Like, I mean, if you want to meet the timing well, you have to enable the primitive resist. Okay. So you have to just enable. So if you disable, you can see this timing as just 1 clock cycle. Okay. Primitive, this clock latency will change. Okay. So instantiation anyway I had shown you yesterday, but let me quickly show you that, I mean, so that like it will be useful. Just okay, COE file is not required. Let me just add this. So as soon as you add, so generate this IP. So here you can see this blocks in, right? So if you right click on this, so here, if you click on the IP sources, and if you click on instantiation template, if you click on VEO, so here you will see that like how to instantiate in your design, right? So you just need to add it to your Verilog code and connect these signals, okay? Like write enable, address, din, dout, all this, okay? Clear? And next one IP, what a very important IP which I would like to show you is PLL. Okay, so then we'll just I'll open a session for like maybe 5-10 minutes per question, and we will wind up. Okay, so in the IP catalog, you search for clocking wizard. Double click on this. So here you can see this is the like see this clock in is from external, or it can be from like processor or something. Okay, so you have like MMCM and PLL, these are the hardcore IP resources. So you have to say that like what is the input frequency. Okay, same way in the output clock frequency, you have to mention what is the frequency you want. Okay, so like 40 megahertz, let's say. So it will show like I mean every time, right? Like all the multiple. So internally it has multiplication and division factor, right? So it may not be able to achieve exact 40. So let's say like I'm requesting 40, it is generating 40 megahertz. So I can generate, let's say like 60 megahertz. So it is able to generate. It will show actually how much it generated. Now let's say I generate 133. Okay. So that kind of odd number, let me try to generate. So it is saying 133 is not able to generate. So it is saying 133.33 it is able to generate. So that kind of thing it will happen. So the deciding of the clock frequency is also very important. Internally PLL may not be able to generate. So in certain cases, if I disable some of the clock frequency, it may be able to generate. So let me disable this. And here 133 if I ask to generate, because like it is a clock multiplication, right? From 100 I am generating 130. See, now it is able to generate. So choosing other clock also is very important because like the PL has to utilize the internal multiplication division factor and it has to generate exactly the frequency, right? So if I go to summary, so it will say that like it used this 100 and clock out. The divider value is 8.75. Then it actually, it is also saying like with this clock frequency, I may have like 215 megahertz, 215 picosecond of clock jitter also, and 269 picosecond of error as well. Okay. So this is the whole, I mean, then like again, add, create this IP and you can interface the same way I have shown, how I have shown for the block memory generator. Okay. Same way you can interface this design into your uh, actual design. Okay, like from external clock, you multiply that clock into higher speed and integrate to your design. Okay, that is the whole idea. So yeah, with that, let me conclude. Let me open for question and answer. So I mean, like again, like I there is like lot to cover. Okay, so I try to fit as much as possible with respect to FPGA in 8 hours. So I mean, basically, this FPGA same course like I take for around 32 hours. That is one course what I take. So this I try to fit into like just 8 hours as much as possible, so that like it will be overview of the whole thing. Okay. So yeah, this is very interesting thing, and like as I mentioned, like there are like lot of scope in case of FPGA system design and like fabless IP design itself. There is lot of scope. Okay. So any questions? Let's keep open for question for the next 5 minutes, and parallelly I'll share you the feedback. Please do fill. I mean that will help us to improve our sessions. So kindly fill those feedback.
A few hints on debugging.
Yes. So with respect to debugging, like as we discussed yesterday's session, so mainly we have to use ILA, integrated logic analyzer. So one is integrated logic analyzer. We have in Altera-based FPGAs, we have like signal tags, and like if you want to debug like high-speed devices, we have something called IBER type, where you can see the I diagram, you can see bit error, you can see EB by N naught. So I'll share you the slide. Yesterday we like whole session was on debugging. I think like
Yes,
yesterday you were
yesterday I
not there.
missed it.
Yeah,
Yes.
yeah. So sure, I'll be sharing PPT to all the participants, so you can go through that. Like it's detailed discussed that.
Sir, anything structure faults in case if there is a faulty FPGA, maybe internally, because I don't know whether they will test for all the LUTs, maybe fabrication
Yes.
side. Something that is,
Fabrication side usually it will not be issue because the all the IPs will be going through DFT test. Like I mean, they'll be testing that. So the FPGA fault is rare. I mean, so far I haven't seen that. Like PCBs will be faulty. I mean, like once we fabricate that, right? So usually these BGA packages, ball grid array packages. So when we fabricate, this will be faulty. But very rarely I have seen that, like from the manufacturing side, this will be defective. Because one round of validation, they'll be defect. Any other questions? Just let me send you the feedback link. Please do share the feedback the whole session, maybe like not only today, all the 4 sessions, so that it will help us to update our future programs. So, I mean, do feel free to contact us also, like info@tanmaya.in. So you can mail us anytime if you need any help in terms of course or like uh, in your projects. So this is a feedback link. Please do submit now itself before leaving the session. I mean, I see that like after leaving the session, like very less feedback we get. So before leaving the session itself, please fill now itself so that it will help us to uh, update. Anything else? Any questions regarding our sessions?
Okay, anybody else who wants to ask the questions?
Sir, one question, sir. In your previous picture diagram, one
Mhm.
terminal is showed as locked. What is the purpose of that terminal, sir?
Locked, is it? Locked.
Yes, sir, locked.
Yes, for the PLL, usually like PLL is like a loop, right? I mean, initially, like as soon as you give the input, so if there is a lock time, like I mean, it's basically you during the architecture of the PLL, if you remember, so there is internally VCX, so there is one VCX, and it keeps multiplying and keep taking the error voltage, right? So when we say the lock is like when the error voltage is zero, correct? So in that PLL, that lock signal indicates it now the error voltage is zero. That means like now you are getting the correct clock frequency. So until the lock signal is zero, high, you shouldn't perform any of the operations. So usually we use that lock signal for our reset generation. So inside the FPGA, we have to monitor that lock signal, and accordingly we have to generate this reset. I mean, once that is locked, then only we have to release the reset for this FPGA device.
So it is one of the way to monitor the error.
Clock jittery. I mean, like once it is one of the way to monitor whether like you are getting a correct clock.
Okay, sir. Thank you, sir.
Thank you.
Thank you very much, sir, for the wonderful knowledge that you have shared here on FPGA and the various dimensions of the same.
Thank you. Thank you very much.
Okay, it's a very good experience, sir. I want to say you from on behalf of E&I CT Academy.
Thank you.
Thank you very much, sir. I hope I will be finding you here in offline mode whenever we will be conducting any workshop or any FDP here based on FPGA or application specific integrated circuit.
Sure, madam. Sure, definitely. We would be happy to be there.
Okay, sir.
Thank you.
Thank you very much, sir.
Thank you. Thank you.